now we have seen a constant volume gas thermometer as a standard thermometer. This is a standard thermometer, means it is not used in all the industrial places, in all the hospitals to measure the temperature, fever of a patient. This thermometer is used to calibrate all other thermometers, industrial thermometers, because it is very costly, heavy, precise, and it takes a lot of time to take the measurements. Now one question is there, if the gas is different in the thermometer, will the readings will be differ or not? So now let us do an experiment in which this is our thermometric bulb of the constant gas volume thermometer. So this is the thermometric bulb which contains some gas. So we have some gas inside it, and when we will put it into a triple point cell, so first we put it into a triple point cell and we measure the pressure at the triple point. So I have measured what is the pressure at the triple point. Now suppose I want to measure the boiling point of water. So again I will put this into the boiling water. So when I put into boiling water, I have to calculate theta, and I will get H to be 273.16 times this P by P triple. So this is at theta temperature, whatever P you got by P triple into this. So in this way I can measure this theta, and I will assign this value of theta to the boiling point of water. This is what we have to do in. Now what we do? So while doing this experiment, we will first measure this pressure. So at triple point, what is the pressure? Suppose in first set of experiment, I found it to be kilopascal, 40 kilopascal. So at triple point, this gas was at 40 kilopascal, and then I found this value something, I got it to be something. Then I will remember this value, I will write this data. Next, what again I will do the same experiment with P triple reduced to 30 kilopascal. So if I reduce this, then this will also get reduced, and finally again I will get a theta value. Then again I will put this, do the same experiment. Each time at triple point, the pressure at the triple point of the gas is reduced. And so in this way I am going to plot a graph between the theta for that water or whatever we are going to do by P triple. So we will plot this curve and we will see what inference we get. So first we put the thermometric bulb into triple point cell, and at that time we take the pressure of triple point at the triple point, and so gradually we will start decreasing this. We will first put the, we will calculate at 40 kilopascal the pressure at triple point, and then we will measure the value of theta at boiling point of water, suppose boiling point of water. Now this experiment is carried out, suppose at this value of, here I have done this, I have 40 kilopascal suppose. So first I will do this experiment with helium, and then next, so I have taken one reading here. So I got the value of water to be something 373.16 or 15 something, I got it. Next I will reduce with the pressure at the triple point 30 kilopascal. Then again I will measure the value of boiling point of water, I get again this value. Similarly if I do with 20 kilopascal, we get the values to be very here, and so it's like that. Now the same set of experiment when I carry with hydrogen, initially the hydrogen gives a numerical value of this much, and as I lower this pressures at the triple point, I get these values. So I draw a graph like this, and when I do this same graph with nitrogen, I initially when the P triple is 40 kilopascal, the reading of boiling point of water is very high for nitrogen, but as I decrease my pressure at the triple point, then all the gases, when this graph is extrapolated, because we may not be able to do this experiment at a very low pressures. So suppose if I extrapolate these graphs, all these graphs meet at a particular point. That means the particular temperature of water, if I am saying boiling point of water, has to be made, then all the gases will give the same reading, provided if I take my triple point pressure to be very small. So all the gases gives the same reading of a particular temperature, provided if the pressure of the thermometric bulb at triple point is very low, i.e. tending to 0. So in this case, all the gas can be used, but you see the best result, the best preferred gas for constant volume gas thermometer is helium, because of two reasons. Number one, at low pressures this gases condenses, liquefies, but helium will remain gas at very low temperatures. Number one thing. Second, hydrogen and other gas tend to diffuse out from the thermometric bulb, which helium does not. So helium does not diffuse at low temperature through the platinum, and second, that it is gas at a very low temperature, whereas hydrogen, nitrogen will get liquefied at higher temperature. So helium is very stable, and this is the most preferred gas for this operation. So now we can define a perfect gas scale as, so theta will be equal to 273.16 Kelvin into that P by P triple, that thing will be there. And if you see P in the limit of P triple tending to 0. So if I consider this limitation, that the limit of P triple tending to 0, that means whatever gas we are using, all will give the same result. This is the value of Kelvin, and the scale in this way defined will be called a perfect gas temperature scale. Later on in second law of thermodynamics, we will see this scale is the same as the Kelvin scale. So now we will see different type of thermometric scales used to measure temperature.